Hello and welcome back. In the previous video, we saw that if p is a prime integer of the form 4k plus 1, which means that its remainder when divided by 4 is equal to 1, there exists an integer z such that z squared plus 1 is divisible by p. Let's consider both these integers as complex integers. Well, since they're real integers, they're automatically complex integers. And we understand that, well, let's write that these two belong to the ring of complex integers. And we know that the ring of complex integers is a unique factorization domain. So let's decompose z squared plus 1 into a product of two complex integers, z plus I multiplied by z minus I, where I is, of course, an imaginary unit, and then decompose each of these expressions into prime factors. So we have a prime decomposition of z plus I. It consists of some complex integer primes, r1, r2, and so on, rl. And of course, the decomposition of z minus I consists of conjugates to these primes. So r1 conjugated, r2 conjugate, and so on, L conjugate. And notice that the imaginary part of z plus I is equal to 1. This means, from this it follows, that none of these primes is a real integer. They all have non-zero imaginary part and also non-zero real part. The same states for these primes, of course, but since the complex integer ring is a unique factorization domain, then p is a divisor of z squared plus 1, which means that p is a divisor of this product here, must also have prime decomposition consisting of these primes. But this means that p is not prime in complex integers. And this is really interesting and really important. Well, p is not prime. We will not find p or any of its associated elements within the set of these r's, of these primes. Well, since p is not prime, in the set of ring of complex integers. And now, since it is so, this means that p has a divisor. P is divisible by x plus y I, where both x and y are integers, of course, and they're both non-zero. And at the same time, the norm of p is strictly greater than the norm of x plus y I, because p is not prime, and this is one of its prime factors. At the same time, norm of p is divisible by the norm of x plus y I. The norm of p as a complex integer is equal to p squared. The norm of x plus yi as a complex integer is equal to x squared plus y squared. So we have p squared divisible by x squared plus y squared. And at the same time, p squared is strictly greater than x squared plus y squared, which is strictly greater than 1. Since both x and y are non-zero integers, so their squares are greater or equal to 1, greater than or equal to 1. So their sum is strictly greater than 1. Okay, so we have a integer, prime integer p, whose square is divisible by some integer, which is greater than 1 and less than p squared. It's obvious that the only way this could happen is if x squared plus y squared were equal to p itself. So this is one of many proofs of Fermat's two squares theorem, or another name of this theorem is Fermat's and Euler's theorem, and we see that it follows from the unique factorization in the ring of complex integers.